This video is an introduction for first-time users of the PicoScope 2204A to help you get started and familiarize you with the basics of using PicoScope software. The PicoScope 2204A is a compact 10 MHz 2-channel oscilloscope with a built-in signal generator designed to be used on a PC running PicoScope software. Before connecting the 2204A, download the latest version of PicoScope software from picotech.com by clicking on the Downloads tab on the home page, then selecting PicoScope 2000 series, PicoScope 2204A. Here you'll find several versions, including beta versions for Mac and Linux, which are fully functional but just lack some of the advanced features that are found in the Windows version. And if we click on this, it takes us to the download page, including release notes and installation notes. Click on download, and while that's downloading, there's a feedback page. And once it's downloaded, press open, and that takes us into the installation. And just keep clicking through next, 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 and then finally install. And it tells us it's successfully installed PicoScope 6. So click finish, and we'll come out of that page. And you'll find the PicoScope software in the start menu in a folder Pico Technology. And at this point, good idea to drag and drop to keep an icon on your desktop for easy access. Next step is to connect your PicoScope 2204 to your PC using the blue USB cable provided. And once that's done, you'll see a red LED between the two input channels. It's illuminated to show that the scope is powered. Next, double click on the icon and the PicoScope window will open. And shows a typical oscilloscope display, which is a graph of voltage on the vertical axis against time on the horizontal axis. There's a blue trace centered around 0, which is the voltage on channel A. And you'll also notice on the scope the red LED is flashing, indicating that the scope is acquiring and sending data to the PC. Above and below the oscilloscope window, there are various menu items and controls, which we'll look at as we go along when we've got a signal attached. But first, let's take a look at the oscilloscope probes that are supplied with the 2204A. The probes are ×1 ×10 switchable passive probes. They're called passive probes because they don't require any probe power, as opposed to active probes that contain circuitry requiring external power. In ×1 mode, the signal passes straight through the probe into the scope without any attenuation, whereas in ×10 mode, the signal is attenuated by 10, which increases the measurement range from ±20 volts peak to ±200 volts peak. So that can be very useful in itself, but the ×10 probes also address another problem. With ×1 probes, the circuit under test is directly exposed to the input capacitance of the scope and also the capacitances in the probe cable, which loads the signal at higher frequencies and may even stop the device from operating properly. A ×10 probe solves this by adding a capacitor network that boosts the signal as the frequency increases. The capacitance of the probe needs to be closely matched to the input capacitance of the scope in order to maintain the 10:1 ratio throughout the frequency range of the probe. And this is why we have a user adjustment in the probe compensation box and why there's a tool provided for the job. So let's start with the probe compensation procedure. For this, I'm going to be using a BNC to crop clips cable connected to the signal generator for an easy connection for the probes. The signal generator output is labeled AWG, which stands for Arbitrary Waveform Generator. We'll look more at this feature shortly. So first, connect a probe from channel A to the AWG, making sure to also connect the ground lead. The probe should be set to ×1. Then switch on the generator output using this icon at the top of the screen and switch on. The default output is a 1 volt 1 kilohertz square wave, which is exactly what we need for the compensation of the probe. We'll explore the generator shortly, but first we need to stabilize the signal by setting the trigger point so that each acquisition and display cycle starts from the same point on the waveform. So let's close the generator and move down to the trigger menu and select Auto. So you'll see a yellow diamond has appeared at the center of the screen, which is the trigger point, and the rising edge of the signal is fixed to this point. The scope does this by monitoring the input signal and capturing the waveform whenever it crosses a set voltage threshold. This is called edge trigger mode and can be set to rising edge or falling edge, like so. Other, more complex triggers are also available in this menu, but for the moment all we require is edge triggering. So the trigger level can be set to a specific value, like so, or moved up and down like so, or just dragged using the cursor and dropped anywhere on the screen. When we move the trigger above the maximum signal level, the scope loses trigger, and in auto mode it refreshes the display once a second with whatever signal is acquired at the time. Whereas in repeat mode it holds the last trigger acquired on the screen and waits for the next trigger to occur, like so. In single, as the name suggests, it triggers once and holds the display until reset using the green button here. ETS mode stands for equivalent time sampling, which is a more advanced concept than this video covers, so we shall leave that for the moment. Just as the trigger point can be set vertically, it can also be set in the horizontal or time axis. By default, the trigger point is set to 50%. in the middle of the time axis, so that to the left of the trigger point is what was happening before the trigger, and to the right is what was happening after the trigger. The trigger point can be moved so that we mainly see either post-trigger or pre-trigger information. Next, we need to set the horizontal scale so that we can see several cycles of the square wave on the display. At the moment, we're set to 20 microseconds per division. The drop-down menu shows all the possible settings, or we can increase the scale gradually until we have several cycles on the display. We're now ready to compensate the probe. At the moment, the probe is set to ×1, so the signal passes straight through the probe without any attenuation. When we switch to ×10, we see the signal gets attenuated and then the vertical scale auto ranges, and we are now presented with a distorted signal that is typical of an uncompensated probe. What we're seeing here is a probe that's not maintaining a 10:1 ratio evenly throughout the frequency range. All that's required is to adjust the variable capacitor in the probe compensation box using the adjustment tool provided until you have a relatively flat top. Now the probe is compensated, it should remain fairly stable as long as you use the same probe with the same channel, but it's good practice to check from time to time. You might now notice that because the probe has attenuated the signal by 10, the vertical scale is now reading 10 times too small. So the next step is to go to the Channel A menu and let the scope know that you have a ×10 probe attached. And the scale will be set accordingly. That concludes part 1 of the PicoScope 2204A tutorial. In part 2, we'll look at the arbitrary waveform generator and other features of the PicoScope software. Thank you for watching.